Hello, this presentation is to make you aware of our utilization-aware power management in reliable and aggressive chip multiprocessor systems. The paper is co-authored by two of my students, Prashad and Prem, and my name is Arun Somani. Let me start with the technology trends and emerging needs. The process technology beyond 32 nanometer is currently facing new challenges under the conventional path of technology scaling. Moreover, the transistor density on a single chip is hitting power and frequency walls. With these trends, the fault tolerance is also becoming important, moving from a nice-to-have property to must-have attribute. Due to these challenges, processors not only need to run fast to deliver performance, but need to remain cool and consume less energy to make use of the available technology. It is our belief that at this juncture, when further improvement in clock frequency is difficult, data-dependent computing provides possibilities to achieve energy, thermal, and performance balance. This research reported makes three main contributions. First, we developed a novel power level switching mechanism using reliable and aggressive design to achieve 40% speed up and 75% energy delay squared savings. We also developed a utilization-aware task scheduling scheme, call it UTS. It's a power management scheme that increases energy efficiency of chip multiprocessors. The UTS, along with the aggressive timing speculation, extracts ample performance without loss of efficiency and breaching power and thermal constraints. UTS improves performance by 12% due to aggressive power level switching and over 50% in ED square savings, according to the results we have shown in the paper. In the rest of the presentation, I'm going to provide you more details of some of the aspects of our work. Let me first start with the aggressive design. Clock frequencies play a very important role in determining the speed up of a pipeline processor. Clock frequency usually is decided based on the process, voltage, and temperature variations, called PVT variations, and that are set for the worst case operating conditions. Earlier in our research, we have shown that aggressive design, employing overclocking, improve performance. However, overclocking may induce timing violation and therefore necessitates additional mechanism for error detection and recovery. In the figure below here, we show two regions for timing errors for various applications on an alpha processor that need to be covered. Incorporating these recovery mechanisms in turn also improves the fault tolerance in the processor against soft errors as well. A side effect of aggressive design is increase in power dissipation, and this is due to additional circuitry needed and increase in the switching activity. So to account for the energy efficiency and find a balance between the aggressive design and power dissipation, we redefine voltage frequency pairs and develop a methodology to use them effectively. Our method called dynamic voltage and aggressive and reliable frequency scaling, DVARFS, is a simple control mechanism. It encompasses two global feedback loops. One is for controlled reliable overclocking, and the other is to control power consumption or regulate temperature. In simple words, the voltage is scaled down to bring the temperature down if the temperature exceeds a critical limit. When the system is below critical temperature, the voltage is scaled up. We implement aggressive overclocking at each of these levels in the system. Now, in order to make use of DVARFS, we also need to understand task characteristics. In order to develop an energy-efficient power management technique, it is important to understand the behavior of standard workloads. Different workloads have different patterns of codes, memory, and input-output uses. We develop UTS as an energy-efficient power management solution for the CMPs. We bring the efficiency constraints to map the set of threads to the core in addition to the existing set of power constraints. This model performs very differently than any of the existing power management techniques. We believe that the power supplied to a core for an application should correspond to the need and not according to the power budget. The figure here shows that when power is supplied as per the power budget, we might be supplying the core excessive power. In order to evaluate the effectiveness of our scheme, we also develop a CMP simulation environment and evaluate the schemes we develop. We use a single core simulation framework using sim out order. We extend this framework to build our chip multiprocessor environment. We assume that the memory is not shared between cores to keep the evaluation simple. The floor plan for the CMP is generated by mirroring and replicating the single core floor plan. Using this framework, we have shown the results which I had already described earlier. The paper presents details of our novel power level switching mechanism, redefining of the existing voltage and frequency pairs, and the performance of our aggressive approach compared to a base scheme with no overclocking. Please read, learn, and enjoy the paper. Thank you.